the previous video, we designed this model and we learned how to design this model in the SolidWorks. We use different sketching techniques and the feature commands to design this model. In this video, in the second part, we are going to use the simulation, static stress simulation. We are going to apply some load, we are going to fix some geometry and apply the load, and we will see if this product will fail under the applied load or not. We use the static stress simulation when we needed to know about the design and about the material under the applied load. If the material is going to fail, if it is a structural member, then we have to look if there is a yielding happening, because after the yielding the design will fail for the structural member. So that's we are going to see in this study. We have to fix these faces, this face and this hole. We have to fix it and we have to apply load here. So after applying the load, we are going to run the simulation and we will see what are the value of these stresses, formation and the strain. So we can use these values to make our observation about the design and about the selected material. So we are going to talk some theory about the static stress simulation, and we have to look uh, what we have to do in the SolidWorks to run this simulation. So I am going to open the design. Next we have to click on simulation, and the simulation tab will appear. We are going to click here and we are going to select the new study. So here in the study type, there are different types of the studies which are available. We can use them. So, but for this one, we are going to use the static stress simulation study. Click OK. So this under the design tree, this tree will appear, which is used mostly for the simulation. So first is the SolidWorks. Here we have to apply the material. So material is given as plain carbon steel. So first thing is that we have to select the material for the stress simulation. Plain carbon steel, apply, close. So material is selected. Then there is the connection. We have to ignore this one. Then we go to fixture. So we have to fix the geometry. We have to, if there is a problem, a specific problem given to you to run the static simulation, you have to basically absorb the geometry and you have to see how this product will act in the actual environment. So for this one, we have to fix these faces. These are the boundary condition. If you have any other specific problem, you have to basically see uh, how this component or the product or the part is acting in an actual environment. What faces are fixed and what faces are not fixed. So you have to make the boundary condition according to the your application. Like if we see in terms of beam, if we see a cantilever beam, this side is fixed. If we are designing a cantilever beam, we have to fix this side, and here we apply a load or at this position. If the beam is supported here and this part is fixed, we have a fixed region here, and for this side there we have a link or a roller here. So we have to apply the boundary condition according to this beam, how the beam is acting in the real application. This is all about the fixture. So you have to decide it for a specific application. For this component, it's given to us that this hole and this face we have to fix it. Next thing is that external load. So we can select force, torque, pressure, gravity, load, temperature, different types of the load. For this application, we are ignoring the gravity. So we are selecting the force, and after selecting the force, this tab, the properties tab of the force and torque will appear here. So we have to select this face. I selected this face, but we have to make some changes according to our required requirement. So the force is acting in that direction. It is not acting like that. So we have to select direction. For the reference, we are going to select the plane. And here we are going to see on which direction our force is. So force is acting upward, we have to change it to reverse direction. And this is given as 5000. Apply OK. At this point, we apply the material, we apply the boundary condition for the fixture and for the load. Next thing is meshing. We have to create meshing. If you know about the finite element analysis, or if you don't know, let me explain it. Basically, in the finite element analysis or in the simulation, we have to divide a component into small elements. So this is what about the meshing. If the components will be small, the time of the solution is large. Like you have to, if you are solving it by mathematically, you have to solve a lot of equations, and it will take a lot of time. But if you keep the element size larger, then it require less time. And if we talk about the SolidWorks simulation or any computational simulation, if you keep mesh size very coarse, like here coarse, that means you are selecting the element size very large. It requires less time, it will take less time and less computational power, and it will give you the solution very um, like early. But for the if you select the element size very small, the solution will be very good. You have like less error with this solution, but it will take a lot of time. It will take a lot of computational power. If you have a laptop which don't have a like graphic card or a strong RAM, then maybe uh, the SolidWorks did not allow you to solve these simulations. So if for the fine element size means smaller size, you have good result, but it will take more time and more computational power. But if you select the course meaning bigger element size, it will give you the result, but this result will have a large error. They will take less time and they will take less computational power. So it is depend on to you what you want to see. Sometimes we just want to know about how this model or the component is going to act according to the applied load. So in that case, course is good. And for the better result, you need to use define. But for this application, we are going to use the default size, which is in the middle of it, and select OK. So you can see meshing is done. Our component is divided into a small component, and now we are going to run the simulation. So let me just we see the summary total elements. You can see we have the total elements and maximum element size, minimum element size. So if we decrease this number minimum element size, you can see we will have more total elements and more nodes. That's why it will take more time. So run this study. After some time, it will show us the result. So after this study, it will show you the stress, displacement, and strain. So according to your analysis, you can like look the result mm, under this applied load and according to the boundary condition. So Sorry, for me, if I look the value of the yield strength and the value of the maximum osmosis stress, we can see the maximum stress value is smaller than the yield strength. That means yielding is not occurring, upper component is not failing under this loading. So if I am a design engineer, I can make the decision for this component, like we can reduce the thickness, we can make the size of this component, the length or the height a little bit smaller, so we have a less material and we will save the cost. Basically, we do this analysis so we can save some material, or if the design is failing, we have to add the material. Or like for this case, we selected the plain carbon steel. So it is very, if we are able to select a material which has less costly but it is fulfilling our functional requirement, then we can select that material and we run this simulation, static stress simulation, and see if the cheap material is uh, okay with the applied load. So we can make the decision according to this result. These are the basic function of using the stress analysis, static stress analysis, and static stress analysis, meaning that there is no motion involvement in this study. We're ignoring the motion and everything related to it. So the component is like still, and we just apply load and we check the result. So using this analysis, I think the the steps are very simple. You just select the load and the boundary conditions. But the main objective of this analysis is, which you have to understand, is understand that why we use this analysis. We use this analysis because we want to know if the specific component is failing under the applied loading, and you have to spend some time to understand that how you are going to select the boundary condition for the specific application, like for a bike frame, which side you are going to fix, for a beam, which faces or sides you are going to fix it, and where you have the applied load for a real product. I think this product is not real. This is just a random product to teach you how to model the design in the SolidWorks and how you can use the static stress simulation, but I am talking about an actual product. Okay, so we can also animate this stress values and see how the stresses are generated in the different region of the object. So if we can see here, the red color is showing for the maximum value. So I think at this point, at this point, we have more stresses, and for the displacement, we can see this area on the top of this circular face, we have higher deformation, and for the strain value, we can see at this point we have more value of the strain. So this is all about how you use the values of the stress, displacement, and strain. For me, like if I am going to talk about this analysis, and see, we let me find the maximum value of the stress. So at this point, we have the maximum value of the stress. So how we can make this side more stronger. So how we can do that, if like you are a design engineer. So basically, what we can do, we can add more material here. If the value of the one mass stresses is greater than, for example, greater than the yield strength. Let's suppose if the value of the one mass stress maximum value, this value is greater than the yielding strength. That means the yielding is occurring. That means this portion is weaker. We have to add some material or some features so that it can support it. So this is the area which is going to have more stresses. So how we can add more support to this value? For example, we can add a rib here, rib like that, which is going to support this value or this stress. Here we add a rib, and then we run the analysis and again see the values of the stresses if it's failing or not. I give this example if the value of the maximum stress is greater than the yielding, but in this case, the maximum stress is under control. It's not greater than the yield strength, and the yielding is not occurring. That means for the structured member, this design is not failing. So let's suppose for another example, we know that the maximum value of the stress is not greater than the yielding strength. So yielding is not occurring. So let's define the factor of safety for this component. So if we see, we have a minimum factor of safety 2.644 in the SolidWorks simulation. If you create the factor of safety, you just have to look for the minimum value of the safety. The higher value of this factor of safety is not usable. It does not make the sums. You have to look for the minimum value for it. So we have to look the minimum value of the stress which is making the sense. The higher value, it does not make the sense, and we are not able to use this value. We have to look for the minimum factor of safety. So the minimum factor of safety is 2.644, and if under the design specification, if if we are told to design a model, a component which have the factor of safety for greater than 3, then this design is not good. We have to add more thickness, or we have to select a stronger material. This is another design consideration. Or if in a case, if the requirement is that we have to design something which have the less value of the factor of safety like 1.5, so we design a component which has the um, value of 2.66. That means we are using a lot of extra material, or we are using an stronger material or costly material. So we can make a uh, decision to select another material which is not costly, or we can also reduce the thickness of these components to make it a little bit smaller, so it can support our design requirement. Because in the designing we also have to consider the cost and the weight of the component. So this is also a design requirement. So I just talk about these things because um, running this simulation is not a difficult thing. You just have to learn some steps and then you can run it. But using these result, it is very important as an engineer or scientific. If you are using this software or the simulation for publication, so these things you must have to make the sense. You have to understand how you are going to use these results. Rest is very easy. These are just some steps you have to follow to apply the boundary condition and run the simulation. The other thing which has great importance in the simulation is about the meshing. So you must have a knowledge of how you can refine the meshes. At some area, like in this first study, we see at this area we have a higher value of the stress, and in this area we have a higher value of the factor deformation. So there is some tools which we can use to make these area very smaller, this area and this area very smaller. So for this area it will give a very refined results. So I think I have to close this simulation. Maybe I am boring you people, so thank you so much. Please subscribe my channel, and if you have any question, please let me know. Thank you so much.